Hello and welcome back to G-Fun Facts Online. Today, we are leaving the surface of the Earth. We are not going sightseeing and we are not going hunting for aliens. We are going to work. Specifically, we are going to talk about a factory. But this isn't a factory that forges steel or burns coal. It is a factory that manufactures life itself, located 250 miles above your head. We are talking about the dawn of space-based tissue engineering. To understand why this is happening, we have to start with the oldest enemy of biology, gravity. For 3.5 billion years, every single cell on Earth has evolved under the tyranny of 1G. We do not notice it because we are born into it. But for a bioengineer, gravity is a nightmare. Imagine you are trying to build a house of cards, but the air pressure is constantly trying to crush it flat. That is what happens when scientists try to grow human tissue in a lab on Earth. Gravity crushes delicate three-dimensional structures into flat pancakes. It forces scientists to use artificial scaffolds, which are rigid plastic or chemical meshes, just to keep lab-grown cells from collapsing into a puddle. This limits everything. It limits the size, the complexity, and the functionality of every tissue we try to engineer in a petri dish. But what if you could turn gravity off? What if you could manufacture the most complex machinery in the known universe, the human body, in a place where biology is finally free to take its natural shape? This is the premise of the new industrial revolution happening inside the International Space Station right now. To understand the magnitude of this, we have to look at the physics of life in microgravity. Biology behaves fundamentally differently when you remove the downward pull. On Earth, growing cells is often called 2D cell culture. You place cells on a flat glass slide. Gravity pulls them down, and they spread out flat, creating a single layer. The problem is that human tissue is not a flat sheet. It is a complex, volumetric structure. A liver cell in your body interacts with neighbors above, below, and to all sides. A liver cell in a petri dish only touches its neighbors on the edges. Because of this, the cell essentially forgets how to be a liver. It changes its signaling and gene expression. However, in microgravity, cells float. They do not settle. This allows them to self-assemble into spheroids. These are perfect, free-floating balls of tissue. They naturally grab onto each other in 3 dimensions, recreating the complex architecture of real human tissue without the need for artificial support structures. This leads us to the scaffolding problem. On Earth, if you try to 3D print a human kidney using bioink, which is a slurry of living cells and nutrients, it will collapse under its own weight before the ink dries. To fix this, Earth-bound scientists print scaffolds made of biodegradable polymers and seed cells into them. But scaffolds can be toxic, they can degrade too slowly, and they physically block cells from communicating perfectly with one another. In 0G, there is no collapse. You can print soft, low-viscosity bioinks that are pure cells and nutrients. The structure holds its shape simply due to surface tension until the cells fuse together. This allows for scaffold-free bioprinting, which is considered the holy grail of tissue engineering. There is also the factor of fluid dynamics. On Earth, fluids are dominated by buoyancy and sedimentation. Heavier things sink, lighter things float, and hot fluid rises, while cold fluid falls. In space, none of this happens. Without convection currents, nutrients move towards cells, and waste moves away from them purely by diffusion. This creates a calm, quiescent environment that is incredibly gentle on fragile stem cells. On Earth, bioreactors have to spin the fluid to keep cells from sinking to the bottom and dying. This spinning creates shear force, which can damage cells or force them to differentiate into bone, because stress triggers bone growth. In space, no spinning is needed. The cells float suspended in their nutrients, growing larger and healthier than is possible on Earth. So what kind of hardware do we use to achieve this? The machinery involved is a marvel of engineering. One of the key players is the Biofabrication Facility, or BFF, owned and operated by Redwire Space. It is a 3D printer roughly the size of a microwave. It uses extremely fine print heads to deposit layers of bio-ink and strengthening structural proteins. Once a tissue is printed in the BFF, it is delicate. It cannot immediately withstand the G-forces of re-entry. It is transferred to the ADSEP, or Advanced Space Experiment Processor, which acts as a smart incubator. In microgravity, the cells fuse, form their own extracellular matrix, and toughen up, becoming a solid piece of biological material. While the Americans favor extrusion printing, which is like a fancy hot glue gun for cells, the Russian program has experimented with magnetic levitation assembly. In their Organ.OT system, cells are treated with a non-toxic magnetic nanoparticle solution. The printer uses magnetic fields to guide these cells into specific patterns in mid-air. In 2018, the Russian cosmonaut Oleg Kononenko used this system to print mouse thyroid tissue on the ISS, proving that complex organoids can assemble in microgravity. But not all space biology requires a printer. We also use tissue chips, or organs-on-chips. These are USB drive-sized devices lined with living human cells. Fluids flow through tiny microchannels, simulating blood. These chips are sent to the ISS to study how specific human tissues like the heart, lung, or kidney react to stress. Because they are small, automated, and data-rich, they are becoming the standard for pharmaceutical testing in orbit. We are seeing history being written with these machines. In July 2023, Redwire announced a historic victory. They successfully 3D bioprinted a full human knee meniscus using the BFF on the ISS. The tissue was cultured in space for 14 days, returned to Earth on a SpaceX Dragon capsule, and analyzed. It was structurally sound. This was the first time a complex, anatomically correct human tissue was manufactured in space. Following this, in 2024, researchers successfully printed live human cardiac tissue samples. Upon return to Earth, these samples were functional. They showed biological coherence that is notoriously difficult to achieve in Earth labs. But why go to all this trouble? Why spend thousands of dollars per kilogram to launch bio-ink into the sky? The potential payoff is civilizational. The first killer application is the organ shortage crisis. In the US alone, over 100,000 people are on the transplant waiting list, and 17 people die every day waiting. The goal is to bioprint organs using the patient's own stem cells, meaning no rejection and no waiting list. The hardest part of printing a liver or kidney on Earth is the vasculature, the millions of tiny capillaries that feed the organ. On Earth, these tiny channels collapse under gravity during printing. In space, we can print the organ and its blood vessels simultaneously and hold them open until they mature. We are starting with cartilage and patches, but the roadmap leads inevitably to full, functional kidneys and livers. The second application is accelerated disease modeling. Space mimics rapid aging. Astronauts experience bone density loss, muscle atrophy, and immune system changes similar to aging on Earth, but at 10 times the speed. By sending tissue chips of bone or muscle to space, pharmaceutical companies can test drugs for osteoporosis or sarcopenia in a few weeks rather than years. If a drug stops bone loss in the aggressive environment of microgravity, it is likely a superdrug for elderly patients on Earth. Then there is cancer research. Tumors are 3D structures. In Earth petri dishes, they grow flat and weak. In space, cancer cells form aggressive, spherical tumors that look and act exactly like tumors inside the human body. This allows researchers to test chemotherapy drugs on realistic tumors, revealing new genetic targets we never noticed in 1G. We are also looking at super stem cells. Research from the Mayo Clinic has shown that stem cells grown in space do not just grow, they improve. They proliferate much faster and seem to retain their potency longer. The vision is to have orbital stem cell farms that mass-produce high-quality clinical-grade cells to be sent down to Earth for treating strokes, spinal cord injuries, and autoimmune diseases. This has birthed a commercial space economy. We have moved past the era where NASA runs everything. Companies like Redwire Space are treating the ISS as a factory floor. Axiom Space is building the successor to the ISS, which will have dedicated manufacturing modules. Blue Origin and Sierra Space are planning Orbital Reef, a mixed-use business park in orbit. Financial analysts project the market for space-based biopharmaceuticals to grow into the billions by the 2030s. Unlike fiber optic cables or exotic alloys, biological tissues have a low mass but incredibly high value. A kilogram of steel is worth pennies. A kilogram of functional human heart tissue is priceless. This makes it the perfect candidate for the expensive logistics of spaceflight. Looking even further outward, there is the Mars connection. If humans are ever to travel to Mars, a 3-year round trip, we cannot take everything with us. In situ biomanufacturing is the future of exploration. We will bioprint meat using animal cells to provide high-protein food. If an astronaut suffers a severe burn, the ship's medical bay will use a bioprinter to grow a skin graft on demand, using the astronaut's own healthy cells. We are even looking at using bacteria to print biological concrete to build habitats on Mars using local soil. However, the road ahead is paved with difficulties. Radiation is a major factor. The ISS is in low Earth orbit, protected largely by Earth's magnetic field, but radiation is still higher than on the ground. If we grow stem cells in space for therapy, we must be 100% sure they have not mutated into cancerous cells due to cosmic rays. Then there is the logistics of the cold chain. Getting a printed heart patch down from space is terrifying. The SpaceX Dragon capsule experiences up to 4 gigaseconds during re-entry and splashes down in the ocean. These tissues must be kept at precise body temperatures or cryopreserved during this violent return trip. A power failure or a temperature spike could ruin millions of dollars of product in minutes. Finally, there is the issue of scalability. Right now, we are printing tissues the size of a coin. To print a full liver, we need large bioreactors, liters of fluid, and massive power supplies. The coming commercial stations are being designed with factory-level power and volume. But scaling up from a localized experiment to mass production is an enormous engineering hurdle. Yet, despite these challenges, the future outlook is incredible. Imagine the year 2035. You are a patient diagnosed with end-stage heart failure. In 2024, this was a death sentence. In 2035, your doctor takes a skin biopsy. Your cells are reprogrammed into stem cells, loaded into a cryocapsule, and launched to Axiom Station Alpha. There, in the BioFoundry module, a robotic arm inserts your cells into a specialized vat. Over 30 days, in the perfect stillness of microgravity, your cells are expanded into billions. They are fed into a massive industrial bioprinter that lays down the complex architecture of a human heart, complete with every vein, artery, and valve. No scaffold blocks the way. No gravity collapses the chambers. 6 weeks later, a return capsule glides through the atmosphere. Your heart arrives by drone at the hospital. It is genetically identical to you. Your body accepts it without a single rejection drug. This is the promise of space-based tissue engineering. It is a convergence of rocket science and biology that turns the emptiness of space into a cradle for life. We used to look at the stars and wonder if there was life out there. Soon, we will be the ones sending it up. Thanks for listening to G Fun Facts Online.